Okay. All right. So it's my pleasure to come back to the beautiful city and talk about this. I think it's a beautiful topic in general, Unitary Bose, I guess. So I want to give a short introduction about why we started this, because not everybody is working on this topic. So everybody sitting here knows that, you know, a Feshbach resonance, right? I mean, schematically represented by this plot. This really opens the door for the studies of very exciting field body physics that being the focus of last couple of days discussions, ephemeral physics, etc. But they also, it's a great platform to study many-body physics as well. So that's my topic will be mainly about the many-body physics, but obviously there's a lot of interplay between few and many, and that's what, you know, that's that was actually the starting point of our study. In terms of many-body physics, I think the most successful story, both experimentally and theoretically, the best studied topic is the fermion superfluid. So you start from BCS. In the many-body case, we call it BCS, and go to the other limit. Eventually, you get the collection of molecules. And this being very thoroughly studied and being, I would say, extremely well understood, both qualitatively and quantitatively, thanks to very many remarkable efforts, you know, numerically understand quantitatively how to think about the thermodynamics in this strongly interacting limit. So this is one of very few systems which are strongly interacting but can be theoretically, you know, very well understood, and even the calculation can be done quite precisely with the help from numerics. And I think one of the reasons is really, I mean, conceptually, I would say what helps us, why we are so successful here is really that if you think about the weakly interacting limit, this is certainly where the BCS theory can be applied. But if you go to the other side, where you can think about the many-body system as collection of molecules, that's also well covered by this BCS trial wave function. So because of that, applying the BCS to the middle of it, you can basically get very good qualitative understanding of thermodynamics, say chemical potential, compressibility. With a little bit more efforts to understand the fluctuation, you can also calculate TC almost by hand, everything. Of course, and those very crude calculations you can compare with the best Monte Carlo, best numerical efforts made, and they are like 20–30% close. And so the trial wave function really help us to understand the physics here. Now, the topic we studied, and of course motivated by many recent efforts on the experimental side, and so this early one was one of the first experiment. Look at the excitation in BEC, but look at the deviation from the simple mean field physics. And this is, according to Carl, was his last experiment on cold gases. And then last few years, especially 2001, afterwards, there are more studies about basically understanding the thermodynamics. So basically, in a nutshell, what people look at is starting from almost non-interacting bosons or weakly interacting, and then understand what happens if you increase the interaction by tuning the magnetic field or scattering length. And so this is the question, sort of relevant, make it relevant to the reality after all these experimental efforts. So as a theorist, I started thinking of this question a couple of years ago, try to understand how to think about the physics beyond the usual dilute limit. Okay, so so I'm going to give a little bit introduction about the theoretical understanding back in 2009 when we started.
Question.
Yes.
Is this a Bose gas or a Fermi gas?
This is the Bose gas. So there's an experiment on the Fermi gas, like Wolfgang Katterli at MIT. They put the fermion there, two species fermion at Feshbach resonance. They were originally looking for the ferromagnetism, the stoner, so-called stoner instability we call it in the condensed matter physics, but basically looking at the possibility when you increase the repulsion between the fermion, whether it's possible that fermion will just go into the same species and form the ferromagnetic state. It's called itinerary ferromagnetism. And of course, nowadays, both experimentalists and theorists agree that it wasn't the right way to think about it. So this is related to what I'm going to talk about, the coupling constant, how to think about the interaction constant, basically. It's kind of a tricky issue. The reason is the interaction, how particles interact, very much depend on which energy scale you look at the problem, especially when you're close to resonance. So basically that's the punchline. And I try to convince you that's very relevant for the many-body study. Okay. So, well, two questions one might ask. One is that, for bosons, generally everybody will think it's a lot easier to simulate than fermion. And the main problem here is that we are mainly interested in this metal-stable physics, right? Everybody in this room, I think, understand this is not a ground state of some Hamiltonian. It's really, we talk about, if you think about at this point, your molecule is here. And then the real ground state for a short-range attractive boson sits at minus infinite. Okay, it's unbounded. So we really talk about condensate sits near the zero energy, and this is what we call a scattering particle, and they live for substantially long time. And we try to approximate the physics within that time scale as equilibrium or thermodynamical physics of these bosons. So that's what we are talking about. So this is, I think, for the people who work on numerics, it's a very interesting issue whether one can do something there. So the first simulation was done, I think, as far as I know, Giorgini tried to simulate the physics back in '95, simulate the physics of bosons interacting with different potentials. So for the other repulsive potentials, either hard wall or soft core, the numerics converge very well. Okay, and the boson Monte Carlo simulation is much more successful than the fermion. But once he turns on the attractive interaction, then it just diverges very quickly. And I think the reason why that simulation is inconclusive is because if you do the standard Monte Carlo calculated potential function, you keep on looking at the physics down here. And it's very, very deep if you really introduce a very short range interaction. So it's very important that, here we want to project at a certain energy scale, and we look at the particular physics at sitting that energy scale within a lifetime. I mean, before this recombination, everything comes in. Okay, so that's basically the issue we want to address and try to provide answers. So this is so before the dilute gas, of course, that's Broglie-Bove theory for the weakly interacting gas. And we now understand Broglie-Bove theory can be applicable to the limit when the interaction are with soft core, so the scattering is in the Bohr approximation. But if you go to the hard core, but still in the dilute limit, when this is satisfied, one have to do the regularization. So the regularization was probably carried out by Li Huangyan and also Baliev using the field theory methods. Okay, and so there have been decades of efforts try to improve the understanding of the dilute gas theory. So this is this equation basically summarizes, almost 5 decades of efforts to go beyond this idea of expansion. So this is the expansion parameter, right? And we basically, this term is Li Huangyan, this is Wu Sawada, and these are the terms studied by Eric. He's not here, and his collaborators. And and also make a connection to the ephemeral physics, etc. So this term, if you write it down, you will see the this log periodic feature there. Okay. So, but what we want to ask ourselves is really if experiments push beyond this limit and beyond the convergence radiance of this expansion, then how to think about this Bose gas. Okay. So that's my short introduction. Both on the theory and experiment is very brief, but that's basically the background. Any questions about this part? Okay. So there are a couple of approaches. The result I'm going to show you at the end of the talk is mainly coming from the effective potential calculation. It's very similar to the, it's basically very similar to the computation done by field theorists, and the early one like by Coleman and Weinberg when they studied the dynamical symmetry breaking phenomena in the field theory models. Except here we are doing the many-body calculation, so the calculation done at a finite chemical potential. But there are also, practically there are also variational approaches. So this idea is really motivated by the success of, to us at least, was motivated by the success of BCS-BEC crossover theory and the BCS trial wave function, the success of application of BCS trial wave function to the lower branch fermion problem. So at the beginning we were thinking whether we can put forward a reasonable wave function which describe to a certain extent the physics in the upper branch. Okay, so it's certainly you have to do the truncation by hand and then looking for the physics there. So these are the early studies of the thermodynamics and chemical potential studies, and these two last work, including the one I think Chris also involved, looking at the even more complicated physics related to dynamics during the sudden quench. So you prepare initial state which is 100% incandescent and ask yourself what happens if you switch on interaction. Okay? So this is in principle, very, very difficult problem. We are not talking about ground state physics. We're talking about some physics sitting near zero energy and try to explore the manifold at that energy scale, right? Okay, so yeah, so in theory we've been keep on asking the following question. You know, we know that we've been very successful in the fermion superfluid near resonance because of the BCS trial wave function. So the question is whether one can develop an analog of that, which capture the main physics in the Bose gas near resonance. But simply, you know, a few lines of equation one can put together and get you the leading correlation. Okay, it might not be exact, but it offers a qualitative picture how to think about those gases. So that's the leading idea. Basically the driven motivation behind all these efforts. Although later on we realized that one can do much better job if one really move towards the fourth spatial dimension, and one can use the epsilon expansion to control the calculation sitting right at the resonance. But at the lower dimension, we still have to use various approximation. But it's at the end, the theorem presents you is self-consistent, which means allows you to do certain non-perturbative things. You know, if you vary the parameter, try to solve the equation at certain interaction strengths to see what you get. Right. So in this sense, these two are sort of along the same line. Both is trying to cover everything within that window from dilute to strongly interacting, but it has to be certain self-consistency or, you know, putting there to make it work. All right. So, I mean, I can talk more about the variational approach and etc. There's certain wave function we proposed in early days. This is called the independent pair model. Eventually, we realized after we did this loop summation, we realized it's become exact and near full spatial dimension. But basically code all the correlation in the two-body channel. And that's our understanding of that variational method now. Okay, so here's what I'm planning to do. I'm going to spend the next 10-15 minutes just talk about why we need to worry about the scale-dependent interaction constant in this many-body problem. Okay, and it's basically a couple of cartoons, hand-waving argument, but I think it's and this argument probably will naturally guide you into the result I'm going to show you. And then I'm going to briefly mention the theoretical framework. This is basically sum up the loops and the various approaches we introduce for different dimensions. Dimension plays a very important role, and we do different things for different dimensions, try to control our theory. Okay. And finally, I will show some results. And for those who are interested in the little bit more details, I think this and the running coupling constant probably was best. The interpretation in terms of running coupling constant was in this long article we wrote, and these three articles mainly about the result coming out of the diagrammatic summation. Any questions? Okay, so this is, I took it from my undergraduate student thesis, asked him to study the resonance 5 years ago. When we try to understand resonance, of course, everybody knows. And the reason I want to show this one is because I'll come back to this one when we compare what we discussed for unitary Bose gas and another strongly interacting Bose gas studied in condensed matter physics, which is liquid helium-4. Okay? But basically, liquid helium-4 to a very large extent can be thought as physics is given by the hot core potential to a very large extent. And if you take those repulsive potential, then your scattering length basically saturates at the range. I take the off order of the range, but if you take the square one, it's just the range of the potential which matters at the end. Okay, and this linear limit is the Boring approximation. That this is the limit where the interaction constant is proportional to the scattering length. But otherwise, for most of the study we do here, or even the hard core, the interaction constant is very different from the scattering. For instance, if you take the hard core, the interaction is infinite, but we know the physical scattering is finite. So this already indicates that if you want to think about the physics outside the Boring approximation one, then do have to worry about how to regularize the theory, etc. Okay, so that's the picture. I will come back to this one and talk about the scale transformation in the real space, but it's basically very intuitive to think that way.
So Fei, you said that liquid helium can be modeled mostly through a hardcore potential, but I mean the scattering length is much larger than the range in liquid helium, right? So what
yeah, so okay, so let me be more precise. I mean, people, of course, numerically, people take into account more realistic potential, like David Shapley did much more thorough studies using the Monte Carlo. But if you want to understand, for instance, quantity like depletion fraction in the liquid helium. So in the liquid helium, it's strongly interacting because 90% of particles are actually outside the condensate. So for that, so there's a famous estimate made by Ansag and Penrose. It's simple, just a hardcore model, and taking the fact that we know the density, and there's an estimate of the range of the potential, you will get depletion fraction estimate from that simple model will give you about 10%, which is very close to experimental 8%. And the other thing is the range is very important there in liquid helium because of the famous Rotan minima in the dispersion. And if you take just a short range model that we do use the contact, you don't have the Rotan minima. Rotan minima, to a certain extent, it's a precursor of the solidification, that your system is kind of very close to solid. You apply a little bit of pressure, you will make a phase transition. So as a precursor of the crystal long range order, if you stay very close to the solid liquid phase transition, the liquid is actually already have a short range of crystallization at a short distance. So if you do the neutron scattering, you don't see the Bragg peaks, but you see around the Rotan minima funny things, a circle around the Rotan minima at the finite wavelength. And so those are the precursors of crystallization. So all those physics has a lot to do with the fact that the liquid helium is very dense and comparable to the range, right, of the characteristic range of your interaction. Of course, realistically, the interaction is van der Waals at the long range, so there's always attraction there. It's still there. But it depends on how accurate you want to understand the physics there. That's what I'm saying, yeah. But certainly because they are so dense, then the scattering itself probably wouldn't have enough space to take place. And that's another very different physics. There, the interaction constant itself is more important. Okay, but
speaking about
yeah, you can.
In liquid helium, there is an interval of temperature which is called semi-quantum, right?
Yeah.
The temperature is larger than the degeneracy temperature, but smaller than the Debye temperature. Do you have in your system the same interval?
Temperature smaller than degeneracy temperature, larger than
Debye,
which is the phonon.
Debye energy.
The phonon defines the phonon window. Yeah, we have. I mean, for the weakly interacting, if I understand correctly.
It happens only strongly.
Yeah. Okay. We haven't thought about that. We haven't thought. Probably the energy scale probably very close, but I cannot answer that question. Yeah. Another way to think about the connection between the gas and the liquid helium perhaps is if you introduce the long range dipole-dipole interaction, and I think some of you study those ones, and then you can create a Rotan minima in the spectrum. You can introduce the Rotan in the excitation spectrum, and so that's another way to think about the range is very important for the physics related to liquid helium. Okay. So this is a cartoon picture of very dry mouth. It's a cartoon picture of to appreciate why we need to think about the scale dependence, especially when we want to understand the unitary gas. So if you think about the model we usually use, I mean, the many body people, that this is certainly not sufficient to understand those physics we talked about yesterday, for instance, the van der Waals, etc., van der Waals length, etc. But for the many body calculation, we usually choose very simple short range of potential, which with very boring feature. But take a short range of potential. Universally, you have this feature in terms of the phase shift. If you calculate the phase shift, the low energy one, you will see the linear k dependence, and the slope tells you the scattering length. That's the definition. But what is also well known is that this is, my way of understanding the universal physics at the two-body level is that once you fix the slope here, you know the whole profile. Once you know the low energy scattering, you know the whole profile up to scale, which is defined by inverse of the range. So if you set the range to be 0, you can basically know the scattering phase shift up to infinite. And that's kind of pretty. And practically for cold gases, the scale set by range is much bigger than the scale set by the degeneracy temperature, for instance. So there's a huge window where, to a very large extent, the physics at a very short distance, we don't have to worry too much, because the only thing that matters is the phase shift. Right? So now here's the question. To what extent, so suppose we have, and we only limit ourselves to the positive scattering length. So the question is, to what extent we can think about positive scattering length as a system with a repulsive interaction effectively, right? So that's the question, and that was also why people look at the fermion and put out a branch, look at the ferromagnetism, right? Because people believe increase the scattering length is effectively increase the interaction, repulsive interaction. So this picture, I think, give a very good answer to that question, to what extent you can do that. And so here I'm just use the hardcore potential and look at the phase shift due to hardcore potential. And I force that at a very low energy they give the same scattering property. So the linear part, they collapse on top of each other, but there's a deviation. The deviation you can show is always occur at one way, at a much lower scale compared to the range of the short range potential. Okay, so that's kind of instructive. So one then can say, so this is basically, you can, the pseudo potential is described with the phase shift here, and at the end, because of this fact, that sometimes we also write for pi times A, especially for bosons, we also write in that way, and then we put in the gross P-Tarski equation, look at the dynamics, everything, right? But this is certainly a very good approximation. And the reason why it works so well is in the usual dilute limit, again, so one way is very large. And so this red line representing the characteristic energy scale of many-body physics. Say for bosons, you should think about the inverse of the heating length, which is much shorter compared to 1A in the dilute limit. And for fermion, you can think about the Fermi momentum, right? And again, in the low density limit, this is very small. So if your many-body physics, the window relevant for many-body physics is here, then you really can do a lot of things by just taking this sample potential. Okay, both for fermion and boson actually. And for instance, the Hartree-Fock, you can get this one, right? And even at the level of Li Huangyan, you don't see a difference between these two. If you do those calculations, you cannot tell the difference between two. Only if you go to higher order, you start to see the difference. And this is all because of the separation of the energy scale in the problem, that you can approximately think these bosons actually are repulsive, although underlying one is attractive. And I think it's kind of a remarkable thing. I never worked on the scattering before, but I think it's kind of a very interesting phenomenon.
This is where your attractive interaction actually has a deeply bound state.
That's correct. It's a positive scattering length, yeah.
So it's the
yes.
phase shift induced by that.
Thank you. Thank you. Yeah, absolutely. I'm interested in the one side of resonance with positive scattering lengths. Correct. The other side is different. Yeah. Okay. And only on that side you can map this one to the repulsion, effect of repulsion. Otherwise you cannot. You don't find a window where these two sit on top of each other. Okay, now everything's hand waving, but I found it's very useful. So this is what happened, I think, in near resonance. If you really want to think about near resonance, you can either think about this window shrinks or this energy scale moving up. But what happened is that the window where you can think about the system as effectively repulsive, suggested by this one, gets very small. And here, the question is how to think about the physics beyond this one way. Right? What shall we call it now in terms of energetics? Okay. So, and at least without doing any calculation, you realize that it's not obvious that what you can do here. But there's a very simple set of arguments one can do to really understand the scale dependence. So what I'm going to do is just show you that here I'm just motivated why we need to worry about the scale dependence because the many-body scale is sitting here, whatever it is, either KF or some energy scale associated with the chemical potential. But if you send one way to be small, then there's always a opposite situation by contrast to what happened in the dilute limit, right? So now we have to quantify a little bit. So how to think about the scale dependence? The first thing one can think about actually is just think about the two particles in a box. And if you put the two particles in harmonic trap, you can even solve it exactly. But let's say that just put in a box as an estimate. And you can either just do the perturbation calculation, or you introduce the phase shift in the box, and then doing the quantization, including the phase shift, right? I mean, you go to the relative coordinate and assume the particle, the relative coordinate living in a sphere or a box, doesn't matter, and then you try to quantize it. using that one. So it's a simple one-particle quantum mechanics. And one then can find out, this is a leading order. In the many-body limit, this is the corresponding to Hartree-Fock. 1 over L cubed converted into density in the many-body limit. But here I just only have one particle in the relative coordinates, so it's 1 over 1 L cubed. Okay, so this is a Hartree-Fock. And the second term gives you the scale dependence, the leading scale dependence when L is much larger than A. So this is a small scattering length limit. You can make a connection with the many-body calculation I showed you before. This one, if you replace L by the healing length, that exactly gives you the Li Huang-Yang correction. The same order, the same parameter which control the Li Huang-Yang, which is square root of Na cubed. But in the two-particle language, it's just 1 over L. Right. So that's the simplest scale dependence one can figure out, and it's very important that one can show the C is always positive. This is very robust, and that's because the phase shift. You know, your phase shift is shifted in a way like a repulsive interaction, and so this is the C is always positive. Right, and that's very important in our calculation. So now if you put in a more formal way, you say I want to introduce interaction constant for my problem. So G2 is basically representing the strength of your short-range interaction, right? Then you can say I want to call the rest of it as my interaction defined the scale of L, or I call lambda. So 1 over L or lambda. Then you can convert it into this expression. And this one really gives you the leading correction at the small scale.
And these two very different things. When the upper line is an infrared cutoff, your L, and this lambda is an ultraviolet cutoff?
No, this is it's the renormalization scale, not the lambda star chord, which is fixed.
Well, but I mean,
this is running.
I guess I should wait how you continue, but I would assume that this you need to do to renormalize the ultraviolet behavior, not the infrared.
Yeah, it's ultraviolet is already renormalized. I use A instead of interaction constant. So that's already regularized in this way. What I express is I'm expressing everything in terms of the zero energy interaction constant. You can also alternatively express everything in terms of the ultraviolet interaction constant.
I don't think anything of that contradicts what I said. But
the question is, what's the role of lambda?
Lambda is just a scale associated with 1 over L. I just converted 1 over L.
Use it as some kind of renormalization group
It's,
scale.
yeah, that's.
So I'm trying to. I think what Hans wants is an interpretation of lambda.
Lambda is in the beta function language is the running lambda. It's the renormalization scale. So you start from lambda star, which is your model. You integrate up to lambda, integrate out. You look at the low energy Hamiltonian. There's a G2 associated with.
So lambda is your UV cutoff. You've integrated everything in shorter width.
In the effect, yeah. For the effective Hamiltonian, lambda is the UV cutoff. Yeah, you can put that way.
But you're going to be interested in running lambda towards 0.
Yeah, yes. I call it a running scale, but it's a UV cutoff after you do the integration, but it's not a UV cutoff in the original problem, which I call the lambda star. Yeah.
Well, that's what we were trying to.
Yeah, I can maybe slightly different.
For instance, when you're rederiving the LHY, if you use the regularized delta function, you don't need a momentum cutoff. You can do all your integrals to infinity.
That's correct. That's because you already regularized it. Yeah. So you basically, instead of using, in the Feynman diagram language, instead of using this V naught, you actually, that's the interaction vertex. But instead of using this one, you use the bubble summation. And you call this whole thing as your box of interaction. And that's for pi A. And this is unrenormalized, this is V naught. And these two, for all the physics we are interested, for the short range, these are totally different.
So you're not going to use from here on?
Yeah, from here on, so you can either express everything in terms of V naught or express in terms of A. And these two are related by the standard regularization, which involve the lambda star thing, the cutoff of the your original Hamiltonian. Yeah. So yeah. Is a standard thing that you can put together. Yeah.
So there you sum over k up to lambda star.
Lambda star, yeah. So this is because this one effectively in my language is the G2 at by rounding equal to 0.
So G2 at lambda equal to lambda star is equal to V naught.
That's correct. Yeah, I'll show you the whole picture later on, but yeah, thank you. Did I answer your question?
Yes.
Yeah, okay. I think there are different ways of writing down the result. But if you express everything in terms of the regularized quantity, then the lambda star doesn't show up. The only thing is this lambda, which is 1 over L in my language. Okay. Okay, so now we can also look at think about what happened at the shorter scale. So this is I go to the opposite limit, L much less than A. And I found that in this limit, perhaps it's a lot easier to just think about the potential itself, because I show you the solution for the square well potential, for instance. And so what one can do is let's sit at the resonance, and then let's rescale the range, and ask yourself how to rescale your potential in order to remain at the resonance. This is basically, it's very similar to Kardanov's real space transformation that used to study the icing critical point. You rescale your system, and you get the same physics out of it, and you look at the transformation between this quantity, right? So it's a really, I like to think about in the real space. I think maybe because of my background in condensed matter physics, it's the real space gives us a lot of things, including the beta function for localization and also critical phenomena physics. But they are equivalent to the Wilson type of the approach. I'll come back to that. But anyway, if you sit at the resonance, if you require, we are sitting at the resonance looking at how the potential scale, you can then look at how the strength scale as a function of the scaling parameter lambda. So that's basically saying the strength scale in the form of length, right? And so then you can convert everything back to the momentum space, just simple using the length and the lambda relation. Then you find out if you think about the smaller momentum scale, then it's related to original momentum scale by lambda. So after carry out this sort of what I call the real space transformation, you will find out G lambda at either you can think about sitting at a resonance, or alternatively you can think about not at a resonance but at a very short distance, because if you stay at a short distance, then the physics you are seeing is very, very similar to the resonance. I mean, it's just like in the critical phenomena. If your distance is smaller than the correlation length, you feel like the system is at a critical point. So very similar ideology. But this is what you get sitting at a resonance. But if you add add larger scattering lengths, you'll get this correction, which I have to get this one, I have to do more careful calculation. But at least it shows you that this is a typical way how scaling argument works. It tells you if you rescale the system either in momentum space or length space, then your coupling constant will have to do certain things so that you produce the same physics. Yeah. Is that a question?
So what's the role of this minus 1 over lambda term there? Can we understand that?
Okay, so one of the way I understand that is if you multiply by lambda here,
Yep.
you produce a dimensionless coupling constant,
And it's a
which
fixed point.
that's a fixed point.
Aha.
Yeah.
I
So
think I recognize this
yeah,
from
yeah.
two-body Pionless scattering in nuclear physics.
okay.
We've been here many years ago.
Okay. Yeah, that's you can formulate everything using the beta function fixed point. There's a scale invariant solution to the beta function, and so the number, of course, you have to calculate it depending on dimensionality. But yeah, in 3 dimensions there are 2 fixed points. One is a weakly coupling. One is this resonance.
So this is the one that corresponds to a system with infinite scattering length.
That's right, yeah.
Okay, I think I know where I am now.
Okay, all right. Yeah, so this is perhaps a more systematic way to capture this one is just Wilsonian language approach to the critical phenomena to understand the scale transformation. You can do everything in the K space and systematically study the beta function. So I think everything will reproduce. Many of you know for years, right? But and for the non-relativistic theory, that's the only thing you have to take into account with this propagated restricted in the shell, and you have to integrate out, and you get the scale transformation. And if you make the shell very narrow, you get a differential equation. So I'm not going to go into all the details. So this part is this is a schematic of that solution, but this part is this part is what I argued before when lambda is very small, right? And it's important is going upwards, and it has a positive deviation from this 4 pi a line. And why it's important, it basically suggests a non-monotonic, because on this side it's 1 over lambda, it's going down. So the coupling constant is non-monotonic. And I think if a coupling constant is non-monotonic, if the coupling constant is described as a solution to the beta function, you can show you have to go through the singularity, and that's, I think, it's a way to think about. Eventually, you have to go through this. It cannot be an analytical function, and that's just observation. If you write on the beta function, you can see that. Okay, so I think what I have talked about is something known to some of you, but perhaps not known to everybody. But I'm going to basically now try to explore what we can learn when we apply this idea to the many-body physics, right? So once you plot this picture, you see clearly that there's a repulsive window. It's what we call effectively repulsive, but this is limited by 1 over A. It's exactly the scale suggested by that cartoon picture of the phase shift. And once you go beyond 1 over A, you're seeing more like the microscopic model you start with, which is attractive to start with. So that makes the unitary Bose gas unique in this sense that the underlying is attractive, because otherwise we won't get a resonance. We won't have all this very fascinating phenomena. It cannot be repulsive from start with. So repulsive is only the low energy tail of the whole thing. But if you're in the dilute limit, you only see this part. You never worry about this. But we have to worry about this because we are going to try to explore the limit that this scale is very small. Now, coming to the fermion problem, this is a very kind of very intuitive way to understand why you put fermion in the upper branch, you wouldn't get the Stoner instability of ferromagnetism that people anticipate at the beginning. Because if you take a scattering lens, this whole thing shifts up, but the window closes very quickly. So if your Fermi momentum is here, you're already seeing the physics totally different from what you anticipate based on 4 pi times A. So indeed, at the end, they found actually molecule formation, even if you start from the upper branch. For that reason, I think it's my way of understanding that experiment. That eventually they are, before the Stoner instability sets in, the system already seeing near the Fermi surface, which is KF, the system already seeing this branch of the interaction. So I try to talk to our experimental colleagues, Wolfgang Katterly and these people. I think this probably is a useful way to think about, the fermion problem as well. Although we never work on that because to sort out that problem theoretically, one have to do, more job. Yeah.
So where do you want to put your many-body scale?
Well, I mean, yeah. So for fermion, you would. I mean, bosons. It's just this bosons is the healing length, 1 over healing length.
So it will be.
It will be. I will show you the result. It's a self-consistent parameter you have to solve. But so you ask yourself whether you will cross here or not.
So this will modify the flow after this scale.
Yeah, I'll come to that. Yeah. It's just showing you that and it's not obvious you think in terms of 4 pi A. That's the only lesson. And the rest you have to do much more careful thing to understand the impact of this red part of the curve, right? Yeah, so yeah, this is what I mentioned before. If you just take this one, look at the small collection, and use this one to calculate the chemical potential. So when you calculate the chemical potential, supposing you're in the dilute limit, instead of using 4 pi times A, you look at the correction, which is this part, deviation from 4 pi times A, and you put in your mean field chemical potential, which is density times scattering length. And this correction to the 0 scale coupling constant will exactly produce square root of Na cubed. And we have done more thorough calculation later on. I will show you what percentage of contribution to Li Huangyan is actually coming from two-body effect. Right? For that, to do the quantity, you have to really look at the diagrams and then attribute some of the diagram to two-body and the other to the four-body, etc., and separate them. And you can do that calculation. In the dilute limit, everything can be done by hand. I mean, not surprising. But this is really how we think about Li Huangyan. So the dominating contribution to Li Huangyan is really the running of the two-body coupling constant.
Yeah, regarding your
I don't know if this conclusion is known to the people in the nuclear physics community, but it's sort of coming out of this analysis. Yes?
regarding your remark on the stone instability
Yeah.
in fermions, so I would imagine, so if I start with a Fermi surface, right, then I would suppose that all the instability will first occur just around close to the Fermi surface. Then if I consider the scattering between two fermions just on the Fermi surface, then the energy difference between them is zero. It should be corresponding to the low end.
That's a party block. Yeah, I think you can work out. I mean, you can work out. Yeah.
But in that
But,
case, why would I identify the effective coupling between them at just a lambda rather big?
I mean, if it's rather big, it's basically everything below the Fermi surface more or less is attractive. I mean, they feel attractive interaction. So there's a Fermi surface reconstruction you have to do, just like in the Cooper analysis. And that's exactly what happened. So alternatively, you can look at the pairing susceptibility, right? And look at which point, at which scattering length, the pairing susceptibility becomes divergent. And there's a point where the pairing susceptibility divergent. That's how, the alternative approach. But it's related to this one. The system overall effectively become attractive. So the quantity I think you really have to calculate is the pairing susceptibility at different scattering lengths, and you will see the singularity at some point. And that's the point that you say, well, the system is unstable with respect to the pairing formation. And that's basically the spirit of the work done by Eugene Daimler and Martin Zwill, and they collaborated. Yeah. My picture doesn't. I don't calculate the pairing susceptibility here. I'm just saying that since you are seeing many attractive, it's natural to think that although you start with the upper branch, at some point, the system is basically feel the same way as in the lower branch.
You say at least overall the energy, the interaction energy is attractive.
That's correct, overall. And how to do the overall, you have to do the calculation. There's sum up all the K and do that, yeah. But there's a Cooper stuff is very robust. I mean, near Fermi surface, the density of state is constant. So if that interaction, if there's a finite window near the Fermi surface is attractive, that's enough to produce the Cooper. Because it's infrared. It's the infrared stability. You cannot kill, right? Okay. So this is, one of the way. So I'm going to show you just one more cartoon picture, and then I will show you the result coming out of the solving those self-consistent equations numerically. But basically, I like this picture because the title of the workshop is a field body, and also a little bit manual body. So it's really the interplay of field body. So now we want to understand what's the implication on the manual body. So for the manual body system, again, as I mentioned, there's a natural scale to separate. So this window basically either is KF or the chemical potential in terms of energy, or the 1 over heating length in terms of length for boson. In the many-body system, there's a window where you have to think about hydrodynamics. And that's the limit opposite to what I talked about before. Because of the chemical potential, it destroys all the argument associated with the beta function. So what I talked about before is very similar to the high energy QED, is that you can apply those arguments up to a certain scale. But if the many-body scale itself, many-body physics has its own scale, then you have to stop somewhere. So the coupling, running coupling constant, you have to, it doesn't flow all the way to all the scale. But that's where you have to, schematically, one of the ways to think about this implication of many-body is, okay, you let the coupling constant flow. So this one is slightly different from the one I showed you before. This is a dimensionless one. And so it's a lambda times g. And so you run to a certain scale, that's the chemical potential. But at this chemical potential, you take the G2 at this scale and use that to calculate chemical potential. So that gives you the self-consistency, right? Usually when we calculate chemical potential, we need to know the G2. But that G2 have to originally set at certain scale, which is associated with the chemical potential. So you can end up with this one. And in principle, you can carry on, include a 3-body. But 3-body also have to, fixed at a certain scale associated with the chemical potential. So calculate the chemical potential. So that's basically the spirit of our self-consistent equation. I mean, when you do this loop summation, it's more abstract than what I'm showing you here, but those calculations, eventually what they indicate is mainly this idea that in the calculation of chemical potential, which I'm going to talk a little bit about details, that your coupling constant itself depends on chemical potential. Okay, so that's basic idea. So that's the matching. I mean, in a sense, what we are doing is matching the low energy many-body physics, which largely we used to know. We know it's controlled by all these hydrodynamics, so it's strongly interacting, and the short distance physics, which is mainly dominated by, say, 2-body, 3-body, right? And which many experts here know more about what happened at a very, very short distance. But what we did is just try to know how to match these two effectively, how to patch these two together.
Sorry, what again are the red lines doing on this graph?
A red line is basically saying, okay, so yeah, I'm using a little bit the language in the critical phenomenon. So this is just one of the gentlemen pointed out. This is basically in the critical phenomenon. In the beta function language, this is a fixed point, which the coupling constant doesn't depend on scale. That's the critical point. So if you tune, so physically, if you take a square wave potential, right, and then sit at the resonance, and if you look at the resonance physics, it's scale invariant. So that's the flow of the coupling constant. Doesn't depend on scale. But if you deviate from that, then the red line tells you how it depends on the scale.
And it's an unstable fixed point. So if you continue all the way down to lambda equals 0, your curve either explodes.
That's correct. That's correct. Yeah. It's an unstable fixed point because it's a critical point. There's a stable fixed point which corresponds to dilute gas physics.
Those flow lines have just been obtained by considering a 2-body system on its own, so they're not in matter.
In this cartoon picture, yes, because once you have many body, this beta function argument doesn't work there. It's like I have a mass for electron, and the beta function only describes the high energy physics well.
Is the beta function you're talking about the standard one of mathematical physics that relates to the gamma function? Or is this some special?
It's a Wilson. It's a Wilson. It's a beta function. Is the function describe the change of the coupling constant?
It's not the beta function.
No.
No. It depends on the system we're talking
about. Yeah. It's not a It's not beta gamma in the mathematical physics, but it's in the Wilson, Gell-Mann law in a sense. Maybe even earlier. I don't know the literature that well, but it's Gell-Mann law. As far as I understand, it's the 1.0 that one. Okay, so that's in spirit what we did, and so basically, if you don't want to know all the quantitative aspect of calculation, one of the easy things to do is you take a chemical potential, you still use this kind of mean field expression, G2 times n. In the mean field, it's 4 pi times a, but in this case, the only change is you have to use the G2 at the scale lambda, and then you approximate scale of the lambda with mu as estimate. What exactly, which square root of lambda you have to choose prefactor, you can only fix by do the diagrammatic calculation more carefully. Okay, it just comes out naturally. But in spirit is really this thing that which kind of give us a good picture about what we were doing with diagrams. Okay, and the mean field is just this one. So in terms of formulation, it's not different. Although in terms of diagrams, this one includes many more diagrams than the vacuum two-body diagram. Okay, because there's a lot of scattering with the condensate which enters. Yes, I'll show you later. Yes.
So this G2 as a function of lambda is a known expression, right? So this is what you.
Yeah. You plug in.
It's just it's an algebraic equation.
That's right. Yeah.
So
but this is.
With three-body.
Yeah. So here is assuming everything. Yeah. Okay. So now that's the place where you have to be very careful. By writing down this way, you basically assume the main contribution is from the two-body channel, but with the renormalized stuff, with all the scattering with condensate included. So there's a way to define G2, but diagrammatically, what kind of diagram you associate with G2. Of course, you can add on top of a G3, etc. We did. We didn't go further to include the four-body, for instance. It's just technically more involved. But the other comment I want to make is the limit. So the limit at which you can solve the problem systematically is the near fourth spatial dimension. Then it's a control. You include all the G2, G3, G4. But G3, G4 itself has a systematic expansion in terms of epsilon. So you can keep them. Okay, I'll come back a little bit more. But here is just really hand waving, and if you just want to get. So again, our motivation at the beginning was to have a theory which will provide very simple, as simple as the BCS-BEC, but capture some dominating correlations in the problem. And we can always refine the process by adding more corrections on top of it. And so the assumption here is we are making expansion around the right channel, okay? And we will include more and more physics there. So that's basically the spirit. So yeah, I mean, this is very naive, but I will show you more, a little bit more involved calculation, the result from that. Okay, so that's basically the end of my cartoons. And okay, so this is very simple equation as you mentioned. So you basically can look at calculate the mu using that self-consistent equation. And here's what you're seeing. Okay, so you get this dashed line is the Li Huang-Yan. It's a benchmark, right? And you start from low energy, you get almost sitting on the Li Huang-Yan, and I can show you the number, how good it is, the two-body, okay? But at some point, we see this one. So that puzzled us for more than 6 months. We didn't understand what happened, but later on, we went through this running coupling constant, we understood that it's because of that. Because the system, at some point, is seeing also the attractive component of the scale-dependent interaction. So the drop here in the chemical potential, eventually you can convert it into related to compressibility, which will actually become negative there. So I should show you more plots, okay? But just that's how we think about this solution. And simultaneously, if you really trust this ansatz, then you can even find out what's the imaginary part of chemical potential. So what's the meaning of the imaginary part of chemical potential? If you write the condensate wave function, you usually write E I mu T and per psi absolute value. So the imaginary part of the chemical potential basically means there's certain damp of your wave function. And we believe that's related to other channel, which the channel we include explicitly in the calculation atomic one, but there are also a lot of other channels down there. They don't show up explicitly in the calculation, but they show up as an environment which described by the imaginary part. So my interpretation is the imaginary part of chemical potential in this case describe how strong it couples with the lower channel. Now, for those who spend a great deal studying the loss rate, I didn't put the field body loss rate here. Okay, in principle, if you really calculate in the dilute limit carefully, even at a very small scattering length, you have imaginary part in the chemical potential because energy density, mainly because we are talking about a metal stable gas which is sitting well above many, many other states. So your energy, and it's a many body, it's not a field body. If you calculate field body, you can get the exact eigenstate, but many body, those states below zero energy, they don't show up, they show up as environment, sort of. And in mathematically in the solution, they show up as this imaginary part. Okay, so if you put the field body loss, you will basically, this singularity will smear out. You get a field body, but there's a sharp rise here associated with this one. So the feature is still there, but it's kind of less singular than what I'm picturing here, right? That's have to be a little bit more careful.
Could you identify that this sharp rise of the imaginary part of chemical potential is associated with the three-body loss?
Right. I mean, it's coming from, I wouldn't associate with just three-body loss because this is coming from, when we do the renormalization, we include a lot of, from the field body point of view, we do include a lot of other processes. It's just not just from the three-body. So.
Okay,
maybe we defer the discussions to the discussions.
Yeah.
We should wrap up.
We are
over. You're already over time.
Okay. So I'm going to show you the result. Yeah. Okay. Okay. Maybe I just spend a little bit of time telling you what we exactly did. Okay. So I can show you a lot of cartoon picture, but what we exactly did is this. Is basically, it's sort of you can think about it in the leading order. Think about the two fluid. You have condensate and you have a quasi-particle system. And you start with assuming you know the quasi-particle mu. So this is again a self-consistent scheme. It's like analog of BEC, BCS, very simple. And then you look at the interaction between fixed number of condensed particle with this so-called reservoir. So this reservoir basically mediated interactions. And this can be proved diagrammatically exactly, but at the end they put in this thermodynamical form. Okay, so this energy density is basically what we calculate. But once you calculate this one, you can apply this condition. You look at the chemical potential of condensate, which itself now depends on the quasi-particle mu. But in equilibrium, if you believe in there's an equilibrium, they scatter back and forth between the two components, reach equilibrium, then this has to be equal to the chemical potential of quasi-particle. So that closes the self-consistent loop. And so the next question is how to get this one. And so that's the main effort was spent on to evaluate that quantity. Right? So it's really, at this stage you see, it's really a close analog of BEC, BCS crossover theory. There's a number equation. And of course this equation, to obtain this one, it's a little bit more involved. But it's kind of variational in spirit. Okay, you want to tune, for fixed chemical potential, you want to tune the number of condensate particles until it's equilibrium. And of course, and that happens when the two chemical potentials equal to each other. All right. So that's basically, this is a 7-body diagram. If you connect all the dots, it's a 7-body. So each diagram, so let me maybe just one word. Each dashed line is the k equal to 0 line. And the internal are the finite k. But all these finite k propagate at a finite chemical potential. So everything you calculate at the end is a function of the condensate density and chemical potential of the quasi-particle. So this is the energy diagram. And then you have to do summation. There's a couple of things we did. And at the end, you obtain that function, which is E, I call it energy density of the condensate, but include all the interaction energy inside. And then you put in and then solve it. And when we solve it, we have to numerically do it, etc. Okay. All right. So this is the quick answer to that question. How much is coming from two-body in the Li Huangyan? So diagrammatically, Li Huangyan is coming from the one-loop calculation, but with arbitrary order of perturbation. So each of this one is just a transition matrix. It's a regularized propagator, regularized interaction. And then you can compute them. So what we did is basically we call everything here is two-body. Of course, when you apply to the dilute limit, you have to include the two-loop, all this sum up. But why it's two-body? It looked like a three-body. But it actually is two-body because this kind of vertex can be removed and simply represented by self-energy, for instance. So it looked like a three-body, but it's reducible. So that's why we call two-body. And so when we calculate three-body, then we have to exclude this diagram. So these are technical details. We struggled for long, try to basically to classify the diagram, organizing in a way we can handle it. And same thing here. This looks like a four-body, but this one is different from this one. This is irreducible four-body. This is a reducible. And this is what we call the two-body, because it's just shifting the energy scale, right? Okay, so two incoming and two outgoing, and then this kind of vertex can be, from classification point of view, it's trivial and can be removed. This kind of vertex involves two incoming condensed line or one incoming condensed line. They cannot be removed by the self-energy operation. So they have to treat differently. So that's how we get it. So these are two. Everything showing is two, although involve five particle coming, 5 particle outgoing, but we call it two. Okay? And this is 4, and this is another 4 here. This is a 5 actually. Well, this 5 can be reduced to 4. So but if you just take this subclass of diagram, and that's what you get. So it's 99.96% of the collective effect actually is simply coming from this scale dependence. It's quite remarkable. I mean, it's a simple calculation, but it's kind of surprising how much you can get out of just looking at the scale dependence. All right. So these are the results. Including more serious calculations. So the blue line is just including the two-body. Some of the diagram I show you there already. Renormalize the two-body. And the red line is further including the three-body, and the three-body effect is not universal. So we also look at how much variation you can get by vary the range of the three-body parameter. So in our model, our treatment of three-body is a little bit naive. We simply add a cutoff somewhere. But this is three-body G3 has a limit cycle behavior consistent with Hans obtained more than 10 years ago. Okay. But then if you look at the contribution from three-body oscillates around 2% near this point where the system become, thermodynamics become funny. Okay, so this is, this is the three-body force, and the real part is the imaginary part. The real part, the imaginary part can be associated with the loss. The real part that I'm plotting here, and what I'm varying is the chemical potential, which is a variational parameter. And so my interpretation is when I vary the chemical potential, I effectively look in the running coupling constant. Okay, and I have this periodic divergency, and the solid line is calculated at the finite scattering length. We can talk more about these graphs if you like, but let me just show you one last graph maybe. So this is a compressibility. If you calculate the compressibility using this approach, you see the rise. Sorry, this is inverse of the compressibility. So mu. Yeah, wondering whether I should look at this one. This is for 2-dimension, but qualitatively I have better understanding of this graph. It's an inverse of compressibility. If you plot compressibility, it shoots up at 0 because compressibility for non-interacting systems is infinite. It's infinitely compressible.
This is 2D, right?
This is 2D, yeah. I'm more familiar with plotting this way. But so this is the inverse of compressibility. Basically, it's a measure of interaction constant. But it's overall interaction. I mean, it's just a total interaction. And increases, so you can think about this as the mean field slope, but then it curve around and come back, go through zero. The compressibility itself, which is inverse of this quantity, means shoots up to infinite. And it shoots up to infinite means the repulsive interaction cancel with attractive. It's strongly interacting, but there's a cancellation. So effectively, it's not interacting. But it's different from the non-interacting here, which is also zero, which is truly non-interacting because there's nothing there. Okay. But then you go to negative, so there's an instability thing. So this is what we consider anomalous thermodynamics in the upper branch, which it's coming out of this analysis. Okay, and that's basically, yeah, I think I will. Should I stop here?
Yeah, maybe it's good if you go to your conclusions.
Okay. Well, this is what I talked about before, the difference between liquid helium and the Bose gas. The Bose gas we deal with attractive interaction, but just to change the scattering length, well, the helium physics is really repulsive to start with, but I mean, in the leading order, and then you basically can vary the range, and you hit some point, you hit this unsagable Penrose point, which is the estimate for liquid helium condensation fraction. Okay, so I'll go down to conclusion. Yeah. So that's our conclusion. Yeah, I didn't put too much emphasis on the first point, but basically saying that the chemical potential written in terms of the Fermi energy is around 80%. That's actually also consistent with the early vibrational calculation. So I think 80% is a good number to think about. And there's an instability associated with it. And for this particular set of problem we study, the Efimov effect in 3 dimensions, it's only a few percent near that maxima. So it's insignificant, but they are there in principle, but numerically it's just, we were looking for those effects, but the numerically wasn't that big. But 3-body effect is very substantial in 2D. We can talk more in the afternoon if you like, but we do include all these 2 trimers sitting below the condensate, looking at those effects. And general statement we learned from this very formal practice is that we look at the 4D. So 4D, the physics is very simple. Basically, the whole condensate can be think about the collection of independent pairs. Within each pair, 2 particles strongly interacting, but pair scattering almost zero. And that's why we can solve it rigorously. But if we look at epsilon, then you find out if you increase epsilon moving away from 4D, general trend is this effect gets stronger. And that's totally consistent with 3D and 4D analysis. 2D analysis. In 2D, we saw stronger 3-body effect than 3D near the same point, near this point of maxima. Okay, so that's the main conclusion. I thank you for your attention. Yeah.
Unfortunately, we're out of time, so I think we defer all questions to the discussion sessions at 3:30.
Mm-hmm.
Essentially, if I understood that correctly, the chemical potential you're treating as a variational parameter in this.
Yeah, so basically in the course of calculation, we have to find the whole dependence of how energy depends on where you put the chemical potential. And then once you get that plot, you solve it. Yeah, so that's basically where if we look at the certain subclass of diagrams, we see that you're running the 3-body physics enter naturally.
So the coupling you have now, usually you always do these kind of things when you have a coupling that runs logarithmically. Now here you have, you don't have, well, at least in 3D, right? In 2D it's different, but you have, as I said, this goes like 1 over lambda plus minus corrections. Yeah. And, so I guess.
Yeah.
So this is kind of that you plotted, right?
Yes,
So
yes, yes, yes. Absolutely. I mean, it's probably you want to make the dimensions, so it's probably yeah.
So I mean, what I mean is that when you do your transformation, the coupling varies strongly if you had a logarithmic running. Is that a problem?
Say it again.
So when you do your when you do a variational approach here, then I mean you have. I mean, it's just that the coupling runs more strongly than if you just had a logarithmic running. So you have larger changes in the coupling, and then.
You mean numerically whether that's a problem? I mean, we did spend a lot of time to solve that. I mean, there's a lot of singularities. There's a lot of singularities.
Yeah. So I'm more thinking about whether. I mean, whether you would think that I mean.
Yes,
you have to do it carefully numerically, but you think that it's a conceptual problem if you have a running that is not logarithmically but runs stronger?
I think for the particular problem we study, probably it doesn't matter whether it's logarithmically or this one. It's a conceptual thing. The only thing is you need two branches. One is attractive, one is repulsive. Basically, if you look at the G2, and you can multiply by density. So 3D you will get this one. 2D you will get.
Yours is a new journal of physics. Yeah. Okay. Yeah, that's what I thought. Yeah, I know. I learned from that.
2D logarithmically look like this. That's 2D. Qualitatively, the structure is very similar. So. And when you solve the self-consistent equation, I mean, it's very hand-waving, but I think it's good blackboard exercise. Basically, you equal this one with mu. So you draw, graphically, when you try to solve it, you draw a line here. That's mu, and you see whether they can intersect. So it's obvious that when 4 pi a is very large, they don't. It's just you have to push this whole thing up, and the same thing to 2D. So it's a conceptual thing. And the reason is that the reason has a lot to do. I mean, the important thing is it's not analytical. It goes to infinite. That's why you cannot find solution. If it's analytical, then you always have something there. So. I think that's not analytical is important for this particular.
So if you were, I'm thinking of something that might be related to what you do, but it's not exactly the same calculation. So if you look at droplet and at n-body droplets, you want to look at large n. So your result for essentially taking n to infinity in the thermodynamic limit is that the two-body effects dominate and three-body makes you a small correction, right? So do you think
right, if that's the case, then it basically suggests our method converging very quickly. But if that's not the case, then yeah, in principle,
do you think that something similar could be true if you look at finite particle number but make n very large?
So we thought I'd like to talk to you more about this. You had a paper with Song and Hammer.
So we did this in 2D. But
we look at the 2D. So it turns out we recently think about that problem more carefully. And we agree with your conclusion. The only thing is that in that case, you mainly focus on the short distance. So you basically use this branch. Which is.
Well, let's say in 2D.
In 2D,
are there also two branches in 2D? I don't remember.
Yes, because you use the attractive part, so it has to be.
Well, you need.
Look at the bounce
you need
so
the bounce states, right?
Your scale is basically binding energy divided by lambda. That's the 2D, right? So what you look at is when this one is larger than this one.
Oh, yeah. So I guess you have to focus on this, right? If you want to have
you really look at the ground state.
Yes.
Yeah. Well, here, but I don't think running slow or fast, whether it might affect numerically, but I think conceptually, it's just that you have two branches. That's the only thing matters, and then you wouldn't able to get anything. But we look at this one more carefully using the 2 minus epsilon. It's actually a remarkable idea, because what we realize is that in all dimensions, either 2 or 1, it's universal. The n-body bound state seems to be universal, and it has a lot to do with the asymptotic freedom. That coupling constant, I mean, the dimensionless one goes to 0, so it's kinetic energy dominated, and at a short distance. So for that reason, it never go to very short distance, because it's like stabilized by that energy associated with the uncertainty. Yeah, but yeah, I think that's the behavior of. And so if you expand it around this point, it's almost the same as this one, around the divergency point.
Okay. All right.
Yeah.
Thanks. So I'm sure there will be many more.
Yeah.
Questions.
Shall I press this one more time?
Sorry.
Do I need to press one more time?
Yes. So.
Okay.